We're continuing our discussion of randomization. So we concluded last time with the discussion of sampling and how to use tail bounds on the behavior of a distribution of a random variable to argue that with with not just an expectation, but with high probability the outcome we want happens. In that case, the outcome we wanted was basically that the estimate of who will win the election from the sample was pretty good compared to the estimate, was an accurate depiction, or at least with high probability was an accurate depiction of who is going to win the election in the overall population. Right? And there's always a probability of error, but as we've seen, because of amplification, you can do these procedures over and over again and reduce the probability of error down to whatever you want it to be. Okay? So that gives you the framework for pretty much how all randomized algorithms work. There is some basic procedure. More often than not, it's a procedure that will have some error. So unlike the first case where we had a procedure that always is correct but has a randomized running time, it's more often the case that you will have a procedure that works in a specific amount of time and has a little bit of error, and then you apply amplification of some kind as you need to make sure the probability of error is what you want it to be. And so you end up with a procedure that works to give you some guarantee on the likelihood of being wrong, but is also hopefully quite fast, especially in comparison to deterministic strategies. So we're going to look at another technique of that kind today, sort of elaborating on that basic idea. Not anything that's particularly new, but an application of that idea where doing something randomized is actually way better than doing something deterministically. And it also gives you a very powerful tool that shows up a lot in, again, a lot of big data kind of data mining type questions. And this is this question of identity testing and also fingerprinting. We'll talk about that today. So let's imagine that we're trying to verify something is correct. Okay, so you will often find that if you want to verify something is correct, randomization plays an important role. So what's something you want to verify? Well, let's say something very simple. Let's say that we have two matrices. They're big matrices, okay? Think of them as very big. And we're given A, B, and C. And you want to verify that in fact, C is the result of multiplying A. So one place where you might think of this as relevant is that you are doing some computation. These matrices are big. As we know, multiplying two matrices can be quite expensive, especially matrices are big. So we outsource this process. We tell AWS or Microsoft Azure, say, hey, can you just do this for me? And then you could rely on them to give you an answer, or you could be a little bit suspicious and say, well, that's all well and good, but I'd like to verify the answer is correct. And they could come back and say, well, fine, multiply it yourself, what do I care? And you're like, the whole reason I asked you to multiply this is because I couldn't do it myself. I wanted you to help me do it. So I want to verify the answer is correct without having to solve the problem myself. And of course, at one level, this is the P versus NP problem. But another level, all I'm asking is, look, you give me your answer, can I do some quick checks to be confident? And in confident, I mean with some reasonable probability that what you've told me is correct. So can I, given A, B, and C, can I verify with a procedure that might have some probability of error, but small, that in fact you have correctly given me the answer to matrix multiplication? Right? So this is the question, how would we do this? And how would we do this without actually multiplying the matrices together? So here is sort of a basic idea, and this exploits some properties of matrices. Right? Suppose I took a vector. I took a vector x, right? So, and I multiplied C times x. Now, multiplying a matrix by a vector is a much easier operation, right? So typically, this will take time that's linear in the size of the matrix. Right? So if you have an n by n matrix and n by one vector, the time it will take to do this is going to be n squared for each row. So I take some vector x and I multiply C times x, and I take the same vector x and I multiply AB times x, but not directly. I first multiply B times x, which is easy and gives me a vector. Then multiply A by that, which is also easy and gives me a vector. I say this very slowly. And I compare these two. Now, of course, if the answer was correct, if C was equal to AB, Cx would be equal to ABx, and I'd be fine. But it's entirely possible that C was not equal to AB, and the x I chose was not a good x, and so they end up being equal. So for example, I would never do this, but if I chose x to be all zeros, then it doesn't matter what C and AB are, it's going to be equal. So so here's a test now. So we can say that we know for sure if it's not equal, then C is not equal to AB. If it is equal, then we're not sure. So this is kind of a one-sided test. If it says they're not equal, we're not like, okay, you fooled me. This is kind of, here's my evidence, you fooled me. Because if C was equal to AB, that should have been equal. But if it says they're equal, we're not sure. And so the question is, can we design a procedure that will give us some degree of certainty, even in the case when it says it's equal, by choosing X cleverly? And of course, if you think, as you should, adversarially, that AWS is actually trying to be lazy. They don't want to waste all their energy on their systems. So when you do ask for AWS, they're like, whatever, just give something. So if you think adversarially that the system is not helping you but is trying to defeat you, then you should also think adversarially, how do you make sure the system cannot defeat you? So one thing that you will come to very quickly is that any fixed X you might pick, so you have a good X in your pocket and you apply it all the time, that's not going to work. Because if AWS ever figures out that you have that X, they will make sure to choose a C, so it might work for that particular X. Right? And then we do that once. So choosing any given X is not going to help you. And the trick is that this is the other way in which randomness helps you, is that if you choose X at random, then the system can't fool you. Or at least we hope that it can't fool you. So the idea we're going to use here to check the system is going to say, so let's assume that these are all the entries. So let's assume that Aij, Bij, and Cij they all belong to some kind of field. Right? So usually the field might be the real or some qualitative, mod some prime number or whatever. So there's some well-behaved thing. And here's going to be the output. So assume these are n-binary matrices. So this is the algorithm. Choose X uniformly at random from the set 0, 1. So each coordinate is either 0 or 1. You can flip a coin probably half. That's equivalent to choosing uniformly. And now just do the multiplication as before. And just return whatever answer you use. If it says they're unequal, you say unequal. If it turns out equal, equal. So of course, one side you know you're correct. And the claim is that now in this particular case, because I've chosen X in this particular way, this side is going to be okay. And in particular, we're going to claim that the probability that so what is this saying? It's saying the probability that ABX is equal to CX, given that AB is not equal to C, is less than or equal to half. So first of all, why do I have to say probability of ABX equal to CX given that AB is not equal to C? Why do I have to put that extra condition there? Why is that important that I have this condition? Why can't I just say the probability that ABX equal to CX is less than or equal to half?
Because we want to find all such X for which the...
No, I just want to find one.
Yeah, but like we want to know how many X's are there for which this condition, this multiplication, the result won't hold.
Right, but why do I put the condition for that? What happens if I drop the condition? I guess that's the question. Suppose I didn't put that condition, assuming AB is not equal to C.
So we are just taking the false positive there. We're not sure what exactly we are checking it. So if you don't have the condition, you're just using the matrix multiplication.
So what could go wrong?
Probably.
Sorry?
The 1 by 2,
Yeah.
which we are checking, we are just checking the amount of false positives. I'm not sure.
Right. But if I drop that condition, so specifically what goes wrong if I drop this condition? I mean, you're very close. You kind of alluded to it. You said you're looking for false positives. If I drop that condition, I could be looking at true positives. If I drop the condition, in fact, AB could be equal to C, then this probability will be 1. So this only makes sense in the context when it wasn't equal and you were looking for false positives. Remember, we are quite happy if the answer to the condition is not equal, then we're fine. The only case we're worried about is when it says it's equal. And the only reason we're worried about it is if this were not equal. If this was equal and these two were equal, that's fine. That's a desirable outcome. This is the case when bad things happen. So we want this event when we had a false positive. That's the event whose probability we want to upper bound. We want to say it's not too big. So we want a less than equal sign. So the conditional is there because that's what we care about. We care about the case when we made a mistake. Because we're not going to make a mistake the other way around. It's never going to happen that ABX is not equal to CX if AB is equal to C. So you'll never have false negatives in this procedure. You only have false positives. And that's what we're trying to figure out. What is the probability of a false one? And so the claim here is that it's less than half. And you might think, well, less than half is not that good. It's pretty large. But again, what do you think then? What do we do if we have a procedure that has, not great probability of error? We use amplification. So you can imagine if I did this, I could choose more than 1x, run it again and again and again. The probability that I get fooled 2 times in a row would be 1/4, if this is true. The probability that I get fooled 3 times would be 1/8. So I can try this as many times as I want to make sure I get the probability of error down to whatever I want. So this is sufficient for now. But the question is, how do we prove even this? Why should this even be true? I mean, this seems very daunting, right? Because you don't know what A is, you don't know what B is, you don't know how they're different. It seems very daunting to argue that no matter what they look like, I can guarantee I don't have a mistake. And this is somehow, in some ways, the power of randomness here, that it allows you to ignore all the issues. If you had to think about this more in detail, you would get lost in all the intricacies of what A, B, and C look like. So let me give you the proof, then you can think about it. So the proof says this. So we know, in particular, that so let's set D equal to AB minus. By assumption, just the condition, we know that D is not equal to 0. Right? Because we just assumed that we're worried about the case when AB was not equal to 0. Without loss of generality, assume that first row of D is non-zero. So again, since D is non-zero, at least some row in D must be non-zero. You can imagine permuting A, B, and C appropriately. We're not actually going to do that. But there is no reason to just make it convenient to say, okay, let's assume the first row is the one that's non-zero. Let's be easier to write things down. You'll see why this won't really matter. It's a proof argument. It's not something we're requiring in the actual code. And also for the same reason, now we permuted the rows, let's permute the columns so that the first k entries of first row are non-zero. And the rest are, k could be at most n, it could be whatever. Again, this is just for convenience to think about how we're going to reason. You'll see why. Okay. So now we can imagine what our D matrix looks like. It looks like something, but it has a bunch of entries here, up to k, and the rest is 0. Okay? All right. So let's assume these entries are, let's we'll give them a name. So we'll call them D1 up to Dk. Okay. And we're multiplying this by some vector x. Right? So we're multiplying this by some vector x. Let's call this E. We can do this because we're multiplying AB by x and we're multiplying C by x, which is the same thing as saying we're multiplying, D by x. Right? So D is ABX by CX. What we'd like to know is the probability that ABX is equal to CX. In other words, what we're looking for and trying to upper bound, the bad event, is the probability that D times X is 0. Right? That's the bad event. Well, if D times X is 0, then the first row of D times X should be 0. The first entry of D times X should be 0. That's the bad event. So what we're asking is, what is the probability that this row times X is 0? Clearly, this must be a lower bound. So if this is, okay, sorry, let me flip it around. Let me ask for the probability that this times this is not 0. Okay, the probability of this being not 0, right, is a lower bound on the overall probability of the system being non-zero, which is the overall probability of a good event. So if we get a lower bound on a probability of a good event, we get an upper bound on a probability of a bad event, right? Does that make sense? So what I'm saying is that, look, the procedure will fail to fool me if that first multiplication is non-zero. There might be other multiplications that are non-zero. I don't care about that. I'm just going with the first one, right? Because there's at least one non-zero thing. So let me look at the probability of this. Okay. So let's write out the expression. What we're really asking now, so notice how we've taken the large event, that ABX equal to CX, and reduced it down to a much more narrow focused event that we can actually hope to evaluate the probability of. And in particular, we're asking what is the probability now that sigma di xi is not equal to 0. Okay? Yes? This is the lower bound on the probability of success. Okay. So now we don't know what the di is on. There could be anything. All we know is something about the x's. So let's do a thought experiment. Let's pretend that we were choosing the x's sort of one by one. We didn't look at d, but we chose the x's one by one at random, uniformly at random, 0 or 1. So now, so let's write out this expression. So we can write sigma dixi is equal to d1x1 plus sigma 2I equal to 2 to k dixi. Why up to k? Well, because we said everything after that is 0. So this is the only interesting one. So we can write this again as, and we want to know if this is, so let's, yeah, okay. So let's ask ourselves under what condition? So when would sigma dixi, I'm going to flip it around again, is equal to 0, which means that d1x1 plus sigma I equal to 2 to k dixi should be equal to 0, which means that x1 should be equal to minus sigma dixi I equal to 2 to k divided by d1. So I just rewrote the condition. The reason I rewrote this condition this way is because you can think of di's, of course, are fixed, right? They're part of the input, but the x's are not. They're something we're choosing at home. So imagine we're choosing the x's sort of one by one, and we chose them sort of in reverse order. So x1 gets chosen the last. You can also argue this the other way around. So you've chosen x1, you've chosen x2, x3, x4, you're doing this all up to xk. At that point, if you now compute this quantity, this is now fixed. You've already made your random choice, then done. So this is fixed and this is fixed. All you have left to do is choose x1. Okay? Now x1 has two choices. It can be the 0 or the 1 for your fee. Only one of those two, at best, is going to match this answer. Right? If I choose an x1, whatever this value is, either it won't match it at all, right? Or if it does, it'll be one of the two values. It can't be both 0 and 1. You can't choose x0, this is 0 and 1 and match at the same time. So at most, one of the two values that you pick for x1 will allow this equation to be satisfied, which will allow their first row to go to 0. Right? So the probability of this happening, so the probability that because at most one of the two values will give you the desired equal. But now we've drilled our high-level event all the way down to this piece. Now we can reel it back up. This basically proves it. That the probability of actually getting a d or getting an x such that dx equal to 0, which means cx is equal to abx, is at most half. And again, remember, this is just looking at one row of d. Because all that d is promised to us is to have one non-zero row. If d has more non-zero rows, this probability gets even lower. Because now lots of things have to coordinate. That's fine. We don't care about that. But we know d has to have one non-zero row. We know it has to have some non-zero entries. And this argument goes through. And that's it. We're done. We now have a procedure that can verify whether the result of matrix multiplication is equal to some target value in time that is much less than actually doing the matrix multiplication itself. And this is the first example of basically how to do verification with randomness. Any questions about this? Again, let me go back up to the top. This was the claim we just made. Yes?
So your proof that and also the dependence on how we choose k. So for whatever value k.
I didn't choose k.
Well, you assume you use some k non-zero.
So it's so think of it this way. That row is non-zero. Right? It has some non-zero entries. The reason I said call it k is because I don't care how many there are. I just need to write down, I need to have a value k so I can write that summation. K could be n, they could all be non-zero. I still don't care. That's what I'm saying, this is without loss of generality. In other words, I just need to say, okay, there are some entries that are non-zero, so I can write that equation. I don't need to know how many there are. So they're like, whatever, call it k, give it a name. That's all. K serves no other purpose in this entire analysis. K could be 1. K could be n, could be n. It'll still work. If you think about it, if k is 1, then again the same argument holds. X has to be 0. Other than 1. So the problem is at most half. If k is more, then it's the same. Similarly, some row have d has to be non-zero. Notice that, again, I didn't care that it was the first row or the jth row. I just did something. So that's the point. So these things are merely analysis artifacts that allow me to say something in a more precise way. But they don't affect, I could write the same proof saying, okay, look, there is some row of D that is non-zero, call that row J. There are some entries in row J that are non-zero. Let's call them entries J1, J2, J3 up to Jk. Then you write the whole thing out into it. It makes absolutely no difference to your argument. This is just a way to make it look clean.
And also the probability of choosing x1 basically can also choosing x2, x3, and
So what I'm saying here is that I am going to not care about how x2 through xk were chosen. Because once they are chosen, you still have to choose x1 carefully. Now, I'm not choosing x1 carefully, I'm choosing it at random. But the chance that x1 lucks out into the exact right value that makes this whole expression 0 only depends on what the previous values were. And they can be arbitrary. In other words, my probability of this happening cannot get me bigger than this. Because this is somehow pretending that the xi's were not chosen randomly. If they're chosen randomly, this gets even better. Because then the chance of this matching gets even lower. All I'm saying is, like, just pretend they're all chosen already. This gives me some fixed target value. I have to hit that target value. So I have only at most one chance in 2 of hitting it. That's it. Another way to say this is that, look, you're doing all these things at random, right? You're picking these things at random. But to have a bad event, the event where it goes to 0, lots of things have to work together. So it's one of those cases where, you know, the bad events are not that common. Things have to synchronize up to really mess with you. But it's hard to argue that deterministically. By doing it with randomness, it's like, okay, look, there's no way it's going to happen. That's the trick, essentially, here. It's a little devious. But again, it's one of those things where the idea is very simple. You know, oh, I want to verify that this is not true. I don't know what x to pick, so I'm going to pick it at random. And that works. And that, you know, again, this idea is very, very powerful, as we will see from one thing. Any other questions about this? What do you
Can you explain how we got the half?
Okay. This half right here?
Yeah.
Okay. So what I said was, imagine the process of picking the xi's, right? Look at only the first row and imagine the process of picking it. So I picked a bunch of xi's, you know, I picked them at random. They have nothing to do with the d, so I picked them. At some point, I picked all the xi's except that first one. Okay. So if all the xi's have been picked, this computation is now well defined. So I got this last one to pick, and I have to pick it, and somehow this magically has to happen. Now this is a fixed value. This is like, you know, whatever, 5, whatever, or 5 divided by something. There either x1 I'll pick and it won't match this, or it might match this. But it can't match it in more than one way. If 0 works for x1 to match this, and 1 is not going to work. If 1 works, then 0 is not going to work. At most, one of the two choices for x1 will allow me to satisfy this. Not exactly one of the two choices, at most one of the two. Maybe neither of them work. But if at most one of the two choices satisfy, what is the probability of picking that choice? It's half. Because I'm picking 0 or 1 is probably half. That's what I said earlier on. I pick each coordinate with probably half. So I only have a half chance of getting this equation to be right, which means I only have a half chance of making this look like it's 0 when it's actually not. And that's why it's half.
And also, with this calculation, it seems like x10 will not be limited to 0 or 1 because.
In this case, I am deliberately limiting it to 0 and 1. In general, you don't have to. But in this case, I'm analyzing it that way. If x could be more numbers, the probability actually drops even further. Because now you have more choices that will go wrong, and only one choice that will go right. There's only one way to get this right. You have to match that value. If I allow x to take more values, then there are more ways it can go wrong, which means this probability instead of 1 over 2 becomes 1 over the space of choices I have. So I'm even happier because the bad event goes down even more probably. But yes, in fact, you could choose it differently. This is the worst possible way from the point of view of the verifier. The best possible way from the point of view of the adversary, but it's still not that great. You had a question?
I have the same question like whether x1 takes only 0 or not.
Does that answer your question? Okay. So this is called Freival's technique for verifying the matrix multiplication, but it applies more generally. It applies more generally because if you think about what we're doing here, we are verifying an identity. We're saying C should be equal to AB, right? So we're trying to verify that there's a general expression around that. So it turns out that this general idea works even for things that are not matrix multiplication. So let me give you an example. So imagine that I have, let's call this polynomial identity. So imagine that instead of matrices, I now have some arbitrary polynomials. Okay. So I have some polynomial P1 in X, and I have P2 in X, and I have P3 in X. These are all over some field, and let's say they're all of maximum degree. Okay. Now, suppose I want to verify and imagine again in general that, so one way I could do this is to say, oh, I'll just look at the coefficients of P1, look at the coefficients of P2, do the whole multiplication, again, verify this manually. But maybe I can't do that. Maybe it's too expensive to multiply them. Maybe there's just too many coefficients to write down. Maybe all I have is some kind of black box access to P1. So all I'm allowed to do is say, hey, what is your value on 5? What's your value on 6? I can evaluate the polynomial, but I can't write it down. This actually happens more often than you might think. That you have access to some polynomial, you can evaluate it, but you can't have actually write it all down explicitly. So all I have is black box access to these polynomials. I can ask them as many questions as I want, but I need to verify that this is true. And again, you can think, well, how am I supposed to check if they're equal if all I'm allowed to do is ask a couple of questions? And again, you might think, well, maybe this randomness idea might help us, where I might do something like pick some x at random from some domain. We'll have to figure that out in a second. And then check if P1x times P2x is equal to P3x. So that particular value of x. Right? And if it is, say, okay, fine. Now again, just like before, if they were in fact equal, this will not be a problem. Life will be good. It will always work. But if they're not equal, you're worried that this might cause a problem. And now the question is, how do we analyze the behavior of this randomized output? So if you have two polynomials of degree p, what is the degree of their product? What does it mean for a polynomial of degree 2? That means the term with largest degree is degree 2. Huh? 2D. 2D. Sorry. Also known as d squared. Sorry. So consider the polynomial q equal to, again, p1, p2 minus p3. Okay? Q has degree 2D. Okay? All right. How many distinct values of x would set Q to 0? Well, one way of asking this question is say, what are the maximum number of roots that the polynomial Q might have? If Q is a polynomial of degree 2D, how many possible roots can it have? This is the fundamental theorem of algebra. A polynomial of degree 2D can have at most 2D roots. It cannot have more than 2D roots. Okay. This is a polynomial of one variable. If If you have a quadratic function, it has two roots. It might be the same, but it has at most two. It's 3, you have 3. You have 4, you have 4. Some of them may be complex, but at most 4. Okay. So we know now that there are 2D different values of x where q could be 0, assuming that q is not identically 0. So again, we have this conditional, right? We are worried about the case when q is in fact not 0, but when we evaluate on any particular value, it is 0. If q was identically 0, then of course it will be 0 for all values of x. This counting would make no sense. But if q is not 0, then the number of places where it can be 0 is very, very small. It's 2D. So let me write this down. So if q is not equal to 0, then if s equal to the set of all x such that q of x equal to 0, then the size of s is at most 2D. So we have this situation where either the polynomial is 0 for every value of x, or the polynomial is 0 for 2D values of x. There's nothing in between. There's a huge gap here. Okay? Everything or 2D. And this gap is what's important here. Because what we're saying is that, look, if it's not the thing we're looking for, then there are only 2D ways that a choice could fool us. Which means that we can choose from a big enough set of things. So fix a set S, which is a subset of a field, right? Pick X uniformly at random, and I use shorthand for that. Then the probability that Q of X is equal to 0 is less than or equal to 2D over the size of X. So again, remember, again, I should have put the conditioning, so it's implicit, conditioned on Q not identically equal to 0. Right? This doesn't do it. Again, what we're saying is that if a polynomial is not identically 0, then it starts wiggling. So 0 polynomial is 0, fine. But if it's not, it starts wiggling. And if it has degree 2D, it can only wiggle sort of 2D times. It can only cut the x-axis 2D times. Right? So we have this picture in our head now of this polynomial. Sort of wiggling around. Right? And it has only a specific number of spots where it's 0. Okay? And now we're saying, well, we're going to choose from a set that has a bunch of things everywhere, including maybe some of these. We don't know. But the probability of picking one of those purple things, if we have enough of the green things, cannot be very high. It's 2D over S. And again, you should think of what happens if this polynomial goes to 0. It's like this thing gets stretched out and it becomes flat. At that point, everything is purple. And so this doesn't work anymore. But that's a good case. The case is not, it's going to wiggle. So it either wiggles 3 times or slide. Okay. So this is a much more general statement, right? Saying, look, if I can combine, if I can check, it came from multiplication, that's fine. But what it's saying is that if I have a polynomial of degree, in this case 2D, but whatever degree, and I want to check whether it's identically 0 or not, I don't have to look at the polynomial. I don't have to evaluate a whole bunch of things. Just knowing what its maximum degree is, I merely need to sample from a large enough set so that that probability goes down to whatever I want to. So you're doing one evaluation, really. Just one evaluation of that polynomial tells you whether it's identically 0. So it's like a miracle almost. I'm asking if it's 0, I do one check and that's enough to tell me if it's 0 or not. All because I have this problem. And polynomials are kind of special that way. They have this big dichotomy between either touching it very few times or touching it all the time. And that's why polynomials tend to be very powerful in randomness, because they have this nice structure. That the number of witnesses of the polynomial being well behaved is very large. So I just going to come down. Right? So this gets you into this whole world of what is called polynomial identity testing and a whole bunch of other things. And one cool trick, let me see if I can show you a cool trick here. Okay, so let me first generalize this. So everything I described to you right now works for polynomials that are univariate. They have one variable x. Suppose my polynomial is multivariate. Suppose my polynomial looks like this. My polynomial is p x y z is equal to x cubed y squared z plus 7x y z cubed minus 23 z or something like this. Suppose this is a polynomial that I can check, and I can't write this down. In fact, if you think about this, the number of terms of this could be really, really big. How do I now check if a polynomial like this has this property of being identically zero? So first of all, let's define some terminology. We will say that the degree of a term in one of these polynomials is the sum of the degrees. So this term has degree 6, this term has degree 5, and this term has degree 1. You just add up the powers of all variables. And then the total degree, so the total degree of P is equal to the max degree of a term. So the total degree of P in this case would be 6, because the max degree of any term is 6. All right. So now here's a very nice result. This is due to well, many people, but it's often called a short-simple lemma. It's also called a short-simple Lipton, one more operating. So it's called a short-simple lemma for now. It says that suppose Q on a bunch of variables x1 to xn. Has total degree D, and is defined, and Q is defined over some field on x1 to xn. This just means that the coefficients of the terms are drawn from some field. The probability that Q of, let's say, R1 to Rn is equal to 0, given that Q is not identically 0, where where R is chosen uniformly random from some set which is a subset of F. The probability of this is less than equal to. So this is a generalization of what we said earlier, but it works for multivariate polynomials as well. And this is a little bit harder to prove, but it basically just, in fact, it's a proof by induction. By induction on the number of variables in the polynomial. So eventually you get down to one univariate polynomial and you apply this previous one. It's not too hard to show, but it takes a bit of work. I won't prove this here. So this you can think of as a generalization of the previous result to the case when you have more than one variable. You define the degree of property and you can do this. And once you have this, lots of interesting things start happening, because now I can try to express a property of my problem or what I want to solve as some kind of polynomial identity testing, and then use this lemma to prove what I want. And so in the few minutes we have left, I'll outline what that looks like. So let's say I have a graph. So I have a graph, and if you remember a matching in a graph, we talked about this in bipartite graphs. So matching is a graph is a set of edges that are all disjoint, right? And so they pair up vertices. A perfect matching is one where every single vertex is paired up. Right? So if I have an arbitrary graph, it doesn't have to be bipartite. So let me draw an arbitrary graph, and maybe it looks like this. It has to be even, of course. I'm cheating, this is a bipartite graph. So let me not cheat. Let me see if I can do this. Okay, let me just. Okay? Then there is a matching that looks like this. Right? It's a set of edges that is disjoint. They cover all the vertices, so it's a perfect matching. Right? If the graph is bipartite, we can find a perfect matching if it exists using Maxwell's. We've already seen this. If the graph is non-bipartite, then it's much harder to find the perfect matching. This is in fact a very famous algorithm. One of the first algorithms that was called a polynomial type algorithm, where the name polynomial type came from back in the 50s. But it's much more complicated. So it's not an easy thing to do. So given a graph, I'd like to know how to compute a perfect matching. But maybe I can ask a simpler question. Does the graph even have a perfect matching? Let me not worry about whether whether I need to compute it or not. Let me just ask, does it have one? Right, so for example, if I have a graph like this, let's see. Oh, this is a bad example. This graph does not have a perfect matching. Yeah. So I'd like to know for a graph, is the answer yes or no? Does it have a perfect matching? I don't need to have the matching, I just want to. And let me show you how to do this using polynomial identities. This is kind of very, very clever.
You said that we have to choose the edges as if they are not continuous, right?
They don't, no two edges overlap. So the matching basically means you pair up vertices, right? So these two are paired up, these two are paired up, and these two are paired up. You can't have this and that, then who's paired up? So let me do the following. Let me construct a matrix in the graph. So I'm going to construct a matrix. Let's call this matrix A, and it's going to consist of A to the Aij. So we'll give it a value. We'll give it a variable. The entry of the matrix will be the variable xij if ij belongs to the edge set, and it'll be 0 if not. Okay? So in this case here, let's say I call them 1, 2, 3, and 4. The A matrix might look like, so there's an edge from 1 to 2, right? So this would be first row, second column. There's no edge from 1 to 1, so we have zeros everywhere here. So it would be x, 1, 2. There's 2 to 3, so that's x, 2, 3. There's 2 to 4, so there's x, 2, 4. Right? And am I mistaken? No, that's, and everything else is 0. Okay. Oh, sorry. I think there was a mistake. One second. I think I made a slight mistake. I think it's retrievable. I did make a slight mistake. So let me take a simpler version of this problem. Let's assume the graph for now is bipartite. Okay, so let's assume that. Sorry. Let me just. Okay. So let's assume for now that G is. I know we can compute the matching using flows, but let's show you a simpler another way of thinking about this. That G be bipartite. Okay, so then you can write G as basically U, V, and edge set between them. So just like before, A is a variable xij if ui to vj is an edge in V. So from left to right, okay? And 0 otherwise. So again, in this case when so in our example from before, which is actually still correct. Let me write this. 1, 3, and 4. Let me write this properly. So here we have 1, 2, 3, and 4. So this basically looks like the set U is equal to the set 1, 3, 4, V is equal to the set 2, and so our matrix would look like X, there's X1, 2, there's 0 again everywhere, X1, 2, and the ordering is what matters here, because I was worried about before. It'll be X3, 2, so that'll be 3, 2, and X4, 2, and everything else will be 0. So now A is now a matrix of variables, right? Okay. And let us compute a polynomial Q as the determinant of A. So you all hopefully know the determinant of matrices. Right now in a very complicated way by this sort of row-wise expansion. But since the elements of A are variables, the determinant of A, which is a product of an addition of terms, is also a polynomial. In particular, it's a polynomial of degree n, at most n, right? Because every term of the determinant has at most n entries in it. Okay, so, and the cool fact now, since Q is a polynomial, is that G has a perfect matching. If and only if Q is not 0. So again, the claim here is that the graph from which we constructed this matrix, this bipartite graph, has a perfect matching if and only if the polynomial we constructed from the matrix from the graph is non-zero, has at least one non-zero. I see you are now out of time, so I will leave you to ponder the mystery of the statement, and I will continue it next time. But the point I want to make here is that if the statement is in fact true, then in order to check if G is a perfect matching, we have to check that, and that we just learned how to check using randomness. So using very efficient methods, we can check this. Okay, so we'll talk about that.